This set of notes is on square root operations. We are going to take a look at multiplying, adding, and subtracting square roots, as well as rationalizing the denominator. Recall the multiplicative property of radicals, which allows us to write the product of two radicals under a single radical sign. We previously used this property to simplify radical expressions. It is also going to help us multiply square roots. In applying this property to multiply square roots, it is important to realize that only the radicands under the radical sign may multiply with each other, and only the factors outside the radical sign may multiply with each other. The first example is the product of the square root of 50 and 2 square roots of 18. First, multiply the factors outside the radical signs. In this case, there is only a factor of 2 outside the radical sign, so it gets a free ride. Then, multiply the radicands under the radical signs. 50 times 18 is 900. Now, simplify the square root. 900 is a perfect square because 30 times 30 is 900. Therefore, we now have 2 times 30, which is 60. The next example is the square root of 6x cubed times y to the 4th power times the square root of 8x to the 7th power times y cubed. There are no factors outside the radical signs in this example, so we are off the hook there. Multiplying the radicands gives us the square root of 48 x to the 10th power times y to the 7th power. We multiply the factors 6 and 8 as usual, and remember that when multiplying like bases, we add the exponents. 3 plus 7 is 10, and 4 plus 3 is 7. Now we need to simplify the single radicand. 48 breaks into the factor pair of 16 and 3. Remember, we need to pick the largest perfect square that is a factor of 48. The square root of x to the 10th power stays as is because it has an even power. The square root of y to the 7th power breaks into the square root of y to the 6th power and the square root of y. Remember that when you have a variable with an odd exponent, you subtract 1 from the power. Now, take the square roots of all the perfect squares. The square root of 16 is 4. The square root of x to the 10th power is x to the 5th power. And the square root of y to the 6th power is y cubed. The other factors will be rewritten under a single radical sign, and the final simplification is 4x to the 5th power times y cubed times the square root of 3y. Here are two more for us to practice with. The product of the square root of 50x to the 11th power and 2 square roots of 2x can be written as 2 times the square root of x of 100x to the 12th power. Now simplify the single radicand. The square root of 100 is 10, and the square root of x to the 12th power is x to the 6th power. Don't forget about the factor of 2 in the front. 2 times 10 is 20, so our final simplification is 20 x to the 6th power. The product of 3 square roots of 75 and the square root of 6 can be written as 3 square roots of 450. The largest perfect square that goes into 450 is 225. 225 times 2 is 450. It's really good to know your first 16 perfect squares by heart to help you. Therefore, the square root of 450 can be broken down into the factors of the square root of 225 and the square root of 2. Now, take the square root of the perfect square, which gives you 15, and the other factor of 2 stays under the radical sign. Don't forget about that factor of 3 that was outside of the radical sign to begin with. The final simplification is 45 square roots of 2. In the previous set of notes, we discussed simplification rules, and the third criteria was that the radicand can't contain a fraction. If the radicand does contain a fraction, take the square root of both the numerator and the denominator. An example would be the square root of 25/36. Break this into the square root of 25 over the square root of 36. The square root of 25 is 5, and the square root of 36 is 6, resulting in a simplification of 5/6. There are a few things to make note of. If the numerator is not a perfect square, it is okay to have a radical in the numerator in your final simplification. However, if the denominator is not a perfect square, we cannot leave a radical in the denominator. In this case, we have to do what is called rationalize the denominator. Let's look at that next. The square root of 7/10 breaks into the square root of 7 over the square root of 10. The square root of 7 can't be simplified because it has no perfect square factors. This is also true of 10. It is okay to leave the radical sign in the numerator, but we can't leave a radical sign in the denominator. In order to remove the radical sign from the denominator, we must rationalize it. To rationalize the denominator, you must multiply both the numerator and the denominator by the denominator itself. The square root of 7 times the square root of 10 is the square root of 70. The square root of 10 times the square root of 10 is the square root of 100. Aha! 100 is a perfect square. If we take the square root of 100, we get 10 and no longer have a radical sign in the denominator. The square root of 70 will stay as it is because there are no perfect square factors of 70. Always check to see if the numerator can be simplified, though. Let's try a few. The square root of 6/5 must be broken into the square root of 6 over the square root of 5. We cannot have a square root in the denominator, though. So we must rationalize the denominator. Multiply the square root of 5 over the square root of 5. This gives us the square root of 30 over the square root of 25. The square root of 25 is 5, so we no longer have a radical sign in the denominator. The square root of 30 can't be simplified because 30 has no perfect square factors. The final answer would be the square root of 30 over 5. In the next example, the square root of 4 over the square root of 11 does not contain a fraction in the radicand to begin with. But we do have a radical sign in the denominator, so we still have to rationalize it. Multiply the numerator and denominator by the square root of 11. This results in the square root of 44 over the square root of 121. The square root of 121 is 11, so we no longer have a radical sign in our denominator. And the square root of 44 can be simplified because 44 has a perfect square factor. The square root of 44 breaks into the square root of 4 and the square root of 11. Now, take the square root of the perfect square, which gives us 2, and leave the other factor 11 under the radical sign. This gives us a final simplification of 2 square roots of 11 over 11. We now need to set ourselves up for adding and subtracting radicals. Recall that like terms are terms that have the same variable and exponent. When adding or subtracting like terms, you add and subtract the coefficients and the variable and the exponent stay the same. For example, the sum of 7x and 3x is 10x. We can extend this idea to radicals. Like radicals have the same index and the same radicand. The square root of 5 and the square root of 5 are like radicals because they are both square roots and the radicand is 5 in both. The cube root of 5 and the square root of 5 are not like radicals because although they have the same radicand, 5, they have different indices. One is 3 and the other is 2. The square root of 5 and the square root of 15 are not like radicals either because although they have square roots, they have different radicands. One is 5 and the other is 15. If we continue to extend our knowledge of like terms, we can understand that the factors outside the radical sign are added and the index and radicand stay the same. When adding 6 square roots of 2 and 5 square roots of 2, we get 11 square roots of 2. Try 3x times the square root of 3 plus 8x times the square root of 3. 3 plus 8 is 11, so the sum is 11x times the square root of 3. 5 square roots of 5 minus 15 square roots of 5 plus 5 square roots of 5. 5 minus 15 plus 5 is negative 5. So the result would be negative 5 square roots of 5. Take a look at the square root of 50 and 2 square roots of 2. At first glance, it may seem as though we can't add these because they do not have the same radicand. However, we have to make sure these radicals are simplified first. The square root of 50 is not simplified because it has a perfect square factor of 25. The square root of 50 breaks down into the product of the square root of 25 and the square root of 2. Take the square root of the perfect square, giving you 5, and leave the other factor 2 under the radical sign. 5 square roots of 2 and 2 square roots of 2 can now be added and result in a sum of 7 square roots of 2. This slide lets us practice addition and subtraction of square roots that must first be simplified. The first problem is 4 square roots of 27 minus the square root of 48. 27 has a perfect square factor of 9, so the square root of 27 breaks into the square root of 9 and the square root of 3. The square root of 9 is 3, and the other factor of 3 stays under the radical. Don't forget to multiply the outside factor of 4 by 3. This gives us 12 square roots of 3. The square root of 48 simplifies because 48 has a perfect square of 16. The square root of 48 breaks into the square root of 16 and the square root of 3. The square root of 16 is 4, and the other factor remains under the radical sign. We are in business now. Remember, the radicands must be the same. In our case, they are both now 3. 12 square roots of 3 minus 4 square roots of 3 results in 8 square roots of 3. The next problem is the sum of x squared times the square root of 32x and 5 square roots of the product of 2 and x to the 5th power. 32 has a perfect square factor of 16. The square root of 32 breaks into the square root of 16 and the square root of 2. The square root of 16 is 4, and the other factors, 2 and x, stay underneath the radical signs. We also have x squared in the front still as well. This gives us a final answer of 4x squared times the square root of 2x. Now, in the other term, 2 does not have a perfect square factor, but x has an odd exponent of 5 that needs to be broken down into the square root of 4 and the square root of x. The square root of x to the 4th is x squared, and the other factors remain the same. This gives us a simplification of 5x squared times the square root of 2x. Ding, ding, ding! We now have like terms. The final sum after simplifying is 9x squared times the square root of 2x. The last problem is the square root of the product of 12 and y to the 8th power minus y times the product of the square root of y times the square root of the product of 75 and y to the 6th power. The square root of the product of 12 and y to the 8th power breaks down into the square root of 4 and the square root of 3 and the square root of y to the 8th. Take the square roots of the perfect squares. The square root of 4 is 2. The square root of y to the 8th is y to the 4th power, and leave the other factors underneath the radical sign. And we end up with 2 times y to the 4th power times the square root of 3. The square root of the product of 75 and y to the 7th power breaks into the square root of 25, the square root of 3, and the square root of y to the 6th. Remember that there is also a y in the front still. Take the square roots of all the perfect squares. The square root of 25 is 5. The square root of y to the 6th is y cubed. The other factors remain the same. Now, this gives us 5y to the 4th power times the cube root of 3. Remember that when you multiply like bases, you add the exponents. That's how we got y to the 4th power there. We now have like terms and are good to go. 2 minus 5 is negative 3. So we get a final result of negative 3 y to the 4th times the square root of 3. Let's review the key points in this set of notes. A radical is completely simplified when 1. There are no perfect square factors in the radicand. 2. There are no variables under the radical sign that have an exponent greater than 1. And 3. When the radicand is not a fraction. Remember that if you end up with a radical sign in the denominator of a fraction, you must rationalize the denominator by multiplying both the numerator and the denominator by the radical in the denominator. Last, like radicals are said to be like when they have the same index and the same radicand. If they do not have the same index or they have different radicands, then they are not like radicals. When radicals are like radicals, they can then be added and subtracted. If they are not like radicals, you cannot add or subtract them. Remember that you sometimes, in this case, have to simplify the square roots in order to discover that they actually are like radicals, and then you can add or subtract them.